chapter 4 modules is for the course جبر پیشرفته. جبر پیشرفته. Advanced algebra. I have defined the elementary notions concerning here. I defined the notion of left OR module. Excuse me, let me find the yes, left OR module, which is an algebraic structure satisfying these properties. I have defined these notions previous week. Okay, I have defined this notion and some examples of R modules, and also the notion of R module and R module homomorphism, and some examples and some other notions, and some theorems and propositions. I think we start from this. Theorems are mainly similar to the case of groups, and so the proofs are removed, but you can refer to a chapter, the chapter which discusses about groups, and see the proofs of these theorems and propositions. This is because modules are in fact abelian groups with an additional structure. So the techniques are similar to the case of groups. Okay, let me to state this theorem. Let B and C be submodules of a module A over a ring R. Number one, there is an orbital isomorphism B. Intersection C is isomorphic to B plus C. This is a well-known isomorphism in algebraic structures, not only for groups, for rings, and other structures. And number two states that if C is a subset of B, then B on C is a submodule of A on C, and there is an R module isomorphism A. on C on B on C is equivalent to A on B. Unfortunately, I think the picture removed. I try to share again.
You are currently the only person in this conference.
Okay, I think, I hope the problem is solved. And number two states that if C is a subset of B, I stated this one. Okay. And the proof is similar to the case of groups. You can refer to chapter 1, corollaries 1.5.9 and 10. And see the proofs, which is similar to this one. The next theorem states that if R is a ring and B is a submodule of an R module A, then there is a one-to-one correspondence between the set of all submodules of A containing B and the set of all submodules of A slash B given by C maps to C slash B. Hence, every submodule of A on B is of the form C on B, where C is a submodule of A which contains B. This theorem mainly states about the submodules of A on B. If B is a submodule of A, it states that the submodules of A on B are of the form C on B such that C is a submodule of A. And the proof is similar to theorem, this theorem and this corollary from chapter 1. Dear students, is everything okay? Voice and picture? Any problem? Do you hear my voice? Any problem? No problem. Good, thank you. Next, show that products and co-products always exist in the category of R modules. As you remember, we have defined products and co-products in a general category in the first session. And here we are going to verify the existence of products and co-products in the category of R modules. We will see that these objects, these universal objects do always exist. Theorem 1.11. Let R be a ring and AI a non-empty family of R modules. Product of AI, the direct product of the abelian groups AI, and sigma of AI, the direct sum of the abelian groups AI. Number one, product of AI is an R module with the action of R given by R dot the sequence AI equals the set of the sequence RAI. So the construction of product in the category of R module is of the form. Product of AI is in fact the set of all sequences such this, and we need two operations. The first one is the summation, which inherits from abelian groups, since AI are in fact abelian groups. So the addition operation is of the form, let me write here. We have in fact the product of AI is the set of all sequences AI, but here it is shown by occulot, and I show this by occulot, such that AI belong to AI, I in I. To be product of AI and R module, we have the operation summation, which is defined in this form: AI plus BI, and R dot AI is defined to be RAI, as it is said here. This construction is in fact the product of R modules and the construction of co-product. But about co-product, we have in the next theorem. This theorem is in fact deals with about product, but in this theorem some details are introduced, and about product and co-product we will see them in the next results. So product of AI is an R module, as I said, and sigma of AI is a submodule of product of AI. Sigma of AI it is introduced in the previous page. I think here. No, here, no, not there. In the chapter 1, it has been defined. Let me say what is sigma of I is here. In fact, sigma of AI is the set of all sequences AI in product of AI such that I not zero or only finitely many I. This means that except some finite, all of AI equals zero. For only finite remaining are not zero. It is said here that sigma of AI is a submodule of product of AI. And number 3, for each k in I, the canonical projection pk from product of AI to a k is an R module epimorphism. This canonical projection is an R module epimorphism. Canonical projections are always epimorphism, and so this means that this is a surjective mapping, which is also homomorphism. PK, in fact, maps to each AI to the K. And for each K in I, the canonical injection AK, here AK maps to the sequence AI with this definition. I equals to, if I equals K, this is a K, and if A does not equal K, this is 0. And clearly it is easily seen that LK is an R module monomorphism. Okay. The proof are easy and left as an exercise. Product of AI is called the external direct product. Is there a picture? Someone says that there is no picture. Really? Is this all of your problem? The problem of all? I think it is needed to refresh. Do you have picture, yes or no? Yes means you have picture, no picture. What about others? Please refresh the picture, refresh your page. Okay. Okay. Please inform us when you solve the problem. I'm waiting for no picture. What about the others? Please, if anyone has picture, let me know. There one has picture. There is no picture. The proof is here by theorem 182. There is a unique group homomorphism phi from C2 product of AI. As you see, in all of these techniques, we use the techniques comes from group theory, and depends on chapter 1, and so it is needed to recall the contents of chapter 1 because we use uh, regularly the techniques of group theory. Need to define a group, an R-model homomorphism from C2 product of AI. But since these objects are in fact abelian groups, similarly to the case of groups, we define phi at first similarly to groups by this definition. As you say, there is a unique group homomorphism phi from C2 product of AI, which has been desired property given by phi of C equals to the sequence phi I of C, because each phi of C is in AI, and this forms a sequence in product of AI. This is a well-defined function and a unique group homomorphism. Since each phi is an R module homomorphism, phi of RC equals to the sequence phi of RC, and this is equal to R phi of C. R comes out on the left of phi, R phi of C, and by definition, R comes to the left. This is equal to R dot phi of C, but this sequence is phi of C, and so phi of RC equals to R phi of C, and so phi is an R module homomorphism. This completes the proof. So product of AI is a product in the category of R modules, and therefore determined up to isomorphism by theorem 18173. I do not know really. I cannot solve your problem. I refresh again and again. I think there is someone that support the system. You can connect with the supporter to solve your problem, because it is not the problem of all of you. I see that only one student has this problem, and for this you have to contact with your supporter of the system to solve your problem. Or maybe your net is weak and any other problem. I do not know. I really do not know. The next theorem deals with about coproduct. If R is a ring, AI is a family of R modules, D an R module, and psi I from AI to D, a family of R module homomorphisms. Then there is a unique R module homomorphism psi from sigma of AI to D, such that psi Li equals to psi I for all I in I. Sigma of AI is uniquely determined up to isomorphism by this property. In other words, sigma of AI is a coproduct in the category of R modules. Let me draw the diagram. We have this morphism from AI to sigma of AI, Li, such that for any family psi I from AI to D of R module homomorphisms, there is a unique psi R module homomorphism such that this diagram commutes. This means psi Li equals to psi I for all I in I. So sigma of AI is the coproduct of the family of I. Here is the proof of this theorem. It is referred to theorem 185. There is a unique abelian group homomorphism psi from sigma of di to d with the desired property. given by psi of AI equals to the sigma of psi I of AI, where the sum is taken over the finite set of indices I such that AI differently from 0. Note that since there is only finite many I such that I is not 0, this summation is well defined. So this summation is taken over the finite set of indices such that AI does not 0, does not equal to 0. It is easy to see that psi is an R-module map since H psi I is an R-module. Maps psi is also an R-module map. Hence, sigma of AI is a coproduct in the category of R-modules, and therefore determined up to isomorphism by theorem 175. Finite direct sums occur so frequently that a further description of them will be useful. We first observe that if F and G are R-module homomorphisms from an R-module A to an R-module B, then the map F plus G from A to B given by A maps to F of A plus G of A is also an R-module homomorphism. This is easy to show that the summation of two R-module homomorphisms is again homomorphism. It is easy to verify that the set home of A and B of all R-module homomorphisms A to B is an abelian group under this addition, which is left as an exercise. Furthermore, addition of module homomorphism is distributed with respect to composition of function, that is h dot f plus g equals hf plus hg and f plus g dot k equals fk plus gk, where f and g are from A to B and h from B to C and k from D to A. Here it is explained about the set of home. Home of A and B is in fact the set of all R-module homomorphisms from A to B. This is an abelian group under this addition, and this has this property h dot f plus g equals hf plus hg and f plus g dot k equals fk plus gk. Note that here is the composition, not product. This is the composition of mappings. It means this means HOF plus G, HF plus HG, and F plus G. OK equals F OK plus G OK. This operation is composition. Okay, let me give a break time and for 20 minutes and come back. Thank you very much. Please rest for 20 minutes and come back to continue.
You are currently the only person in this conference.
position jth component. For example, assume that here is the j. In this sequence, only we have here only AI and all of the components are 0. So the action of Pj on this sequence equals to the element in jth position. So this is 0. And so Pj Li equals to 0. This. And you can do as an exercise the number 3. Likewise, if A is isomorphic to A1 plus dots plus AN under an isomorphism F, then the homomorphism PIF and F inverse Li satisfy 1, 2, and 3. But actually, we do not make a difference, do not admit the difference between isomorphism and equality. I mean, it is not necessary, this the second assertion, because congruent are in fact equality. For the converse, this sufficiency, let Pi from A to A and Li from AI to A satisfy these 3 properties. Let P' from A to N to II and L' from AI to A1 to AN be the canonical projections and injections. Let phi from A1 to AN to A be given by phi equals to L1 P'1 plus L2 P'2 plus Ln P'N, and psi from A to this direction by L'1 P1 plus L'2 P2 plus L'N P10. Phi psi equals to this sigma composition with this sigma, which is equal to this one by the distributivity property. We can write this formula as this form. And this sigma equals to this sigma because by the assumption we have Pjli equals 0 and Pili equals the identity. So this sigma, in this sigma we can not consider some parts that the indices are different. we can put 0 instead of the positions that have different indices, and so we can write this formula as this form. So this is equal to sigma Li Pi, Li P prime I, L prime I Pi from 1 to n. So phi psi equals to this sigma. And this is equal to, since we have P prime I, L prime I equals to the identity, so this is equal to this sigma, and this gives sigma L of Li Pi, which is the identity by the assumption. So phi psi equals to the identity, and similarly, one can prove that psi phi is also to the identity. Therefore, phi is an isomorphism, and so the proof is complete. The next theorem says that let R be a ring and I a family of submodules of R module A such that A is the sum of the family AI for each K in I, AK intersection AK star equals 0, where AK star is the sum of the family AI not equal to K. Then there is an isomorphism between A and sigma of AI. This theorem presents an isomorphism between an R module and a family of the summation of the family of a family of submodules of A. It says that if A is the if AI is a family of submodules of A such that A is the sum of AI and the intersection of AK with any AK star, which AK star is the sum of the family of AI, I not equal to K. Then there is an isomorphism between A and the sum of its submodules. A module A is said to be the internal direct sum of a family of submodules I, provided that A and the family AI satisfy the hypothesis of theorem 150. 150 is this theorem. So we say that internal direct sum. As in the case of groups, there is a distinction between internal and external direct sums. If a module A is the internal direct sum, yes, Zainul Abedin, Mr. Zainul Abedin, I have sent the solution book some days ago, I think. Did not you receive? I think I have sent you. No. Okay, let me check again. Check now. Let me check. Mr. Zainul Abedin. But in this email, I see the book, but not solution book. But I do not know why the solution book is not in our sent emails. Welcome. Yes, let me do this after the class. Yes, I sent. Is it your email, Mr. Zainul Abedin? Yes, okay. Okay. Here in this paragraph, it says that about the difference of internal direct sum and external direct sum. The module A is said to be an internal direct sum of a family of submodules AI, provided that A and AI satisfy the hypothesis of theorem 1.50. As in the case of group, there is a distinction between internal and external direct sums. If a module A is the internal direct sum of modules AI, then by definition, each of the AI is actually a submodule of A, and IA is isomorphic to the external direct sum sigma of AI. However, the external direct sum sigma of AI does not contain the modules AI, but only isomorphic copies of them. Now it is not so important for our subject, and it is sufficient to note this theorem, and if these assumptions hold, we say that A is an internal direct sum of AI. Yes, I am sorry for your problem. Maybe you have to change your net or your system or any other way to solve your problem. Do you have any information about the supporter of the system? When you have a problem in this system, there is someone which can help you you report your problem to the supporter, and they try to solve your problem. In this notation, we write A equals to sigma of AI to indicate that the module A is the internal direct sum of the family of submodules AI. Okay. Here we are going to an interesting notion which is important is in the theory of modules. Definition 1.60. A pair of module homomorphisms A, B, C, F, G is said to be exact at B, provided that image of F equals to kernel of G. Note here that here we have a sequence of module homomorphism. A to B is a module homomorphism. B to C is also a module homomorphism. We say that a pair of homomorphisms in this form is exact sequence, exact at B, if image of F equals to kernel of G. Image of F is the set of all F of A such that A belongs to A. This is image of F. This is a submodule of B. This notation we mean, by this notation we mean submodule. And kernel of G. Kernel of G is the set of all B in B such that G of B equals to 0. This is also a submodule of B. When these two submodules coincide, image of F equals to kernel of G, we say that this sequence is exact at B. Here we are going to generalize this notion for a family of homomorphisms, a sequence of homomorphisms, a finite sequence of module homomorphisms, A0 to A1 to A2 dots to AN minus 1 to AN is exact provided that image of Fi equals to kernel of F of index I plus 1. This means image of F1 equals to kernel of F2, image of F2 equals to kernel of F3, and so on. An infinite sequence of module homomorphisms in this form is exact provided that image of Fi equals to kernel of Fi plus 1 for all I in Z. This definition is for infinite sequence of homomorphisms. Yes, it is said here that we say exact sequence of modules rather than an exact sequence of module homomorphism. We usually remove this word. As for simplicity, we say that exact sequence of modules instead of exact sequence of module homomorphism. Here is some examples. Note first that for any module A, there are unique module homomorphisms 0 to A and A to 0. 0 to A is a unique homomorphism because this only send 0 to 0. And this is also unique because maps any element of A to 0. So these morphisms are unique. If A and B are any modules, then the sequences 0, A directs on B to 0. Here is the canonical injection AI or L, and here is the canonical epimorphism P. And also 0 to B to A plus B to A to 0 are exact. These are examples of exact sequences where the L's and P's apostrophe S are the canonical injections and projections respectively. This is not hard to verify that, for example, this one is exact because let me show this one by this is L. We must show that image of L equals to kernel of P. Why this is equal? Image of L is the set of all L of A such that A is in A. This is equal to L of A is the ordered pair A and 0, in fact, such that A is in A. On the other hand, kernel of P is the set of all A and B belongs to A directs on B such that P of A and B equals to 0. But we know that P of A and B here is it is better to put an and this here. Let me read your messages. Yes, I usually by mouse I show the words on the theorems or paragraphs or words, you can see them. But in some parts I write. Don't you see the formulas which I write? Do you see these formulas? I'm writing something to explain some parts. So here is P and this B, and here is P and this also. P and this B, A and B equals to 0. But P and this B, A and B is B by definition, because it maps to this ordered pair to the second component. So this is equal to, when B is 0, we have the set of, this is the set of all A and 0, such that A in is in A, and so as you see, these two sets are equal. So image of L equals to kernel of P. Do you see the formulas which I write now? Do you see the mouse here now? Do you see? I have written some formula at the bottom of this page. Have you seen these formulas which I write? Okay. So we have in this part, we have an exact sequence. Note here that to be this is exact, it must be L is 1-to-1 and P is surjective. And we know that since this is 1-to-1 or injective, it is an injection, and so it is injective. And we know that projection epimorphism are always surjective. So image of L equals to kernel of P, and I show this. In this part, we must have the image of 0 equals to kernel of L. Image of 0 is 0, but kernel of L is also 0, because L is an injection, and so it is injective. So in this part, we also have the exactness. And also in this part, image of P equal to kernel of 0. The 0 map is the kernel of this map is 0 because the theta is B. The kernel of this map is B, because kernel of this map is the set of all B in B, such that the 0 of B equals to 0. And since for each element of B, we have that B maps to 0, so kernel of this one is equals 0, equals B. So image of P and this B equals to kernel of B. And similarly for the second. Similarly, if C is a submodule of D, then the sequence 0 C I C D D on C to 0 is exact, where I is the inclusion map and P the canonical epimorphism. It is a well-known exact sequence which is useful in somewhere we discuss about this subject. But let me show the exactness of this sequence. 0 C I D P D on C to 0. I is 1 to 1, and so image of 0 equals to kernel of I. If you show this by 0 and this also by 0, image of 0 equals 0 equals to kernel of I, because I is 1 to 1 or injective. On the other hand, image of P, since P is the canonical epimorphism, it is onto, and so image of P is equal to D on C, and the kernel of 0 also equals to D on C. So image of P equals to kernel of 0. It remains to show that image of I equals to kernel of P. Image of I equals to the set of all C to C I of C. The set of all I of C such that C is on C. But I of C is C because I is in fact inclusion map. This is inclusion. So image of I equals to C. On the other hand, kernel of P equals to the set of all D in D such that P of D equals to 0. But the 0 in this on C is C. So this is the set of all D on D such that P of D means D plus C equals to C, and so D plus C equals to C is equivalent to D is in C. So the set of all D in D such that D is in C equals to C. As you see, both of them are equal to C, and so image of I equals to kernel of P. Please answer my question. Do you see what I write? I write something on the file. I do not know. You see my formulas. I do not know. Nobody answered to my questions. Okay. If A from A to B is a module homomorphism, then A on kernel of F, respectively B on image of F, is called the co-image of F, respectively co-kernel of F. B on image of F, if you have an homomorphism, B on image of F is called the co-kernel of F. And A on kernel of F is called the co-image of F. And denoted co-IMF and co-kernel of F. Each of the following sequences is exact. 0 kernel of F, A co-image of F, 0. And 0 image of F, B co-kernel of F, 0. And kernel of F, A, B co-kernel F, 0, where the unlabeled maps are the obvious inclusions and projections. I show one of them, the exactness of, for example, the first one, and the remainder, are left to the readers as an exercise. To prove the exactness of the first one, please answer to my question. Do you see what I write? I write something on the file. Do you see them? Okay, thank you. I'm going to show that this sequence, this one, is exact. We have 0 to kernel of F. Kernel of F is a submodule of A. This is injection L. A to co-image of F. This is the, since the co-image of F is, this one is A to kernel of F. This is the projection map. And at last we have 0. In the first or also we have also 0. Thank you for your answers, but unfortunately, Zaidun Saadun has serious problems. There is no voice and no picture for him or her. Picture is okay. You have you didn't have picture but voice were okay, but it is conversely that you have picture but no voice. I do not know. I do not know what is the problem. In this part, I wish to show that this sequence is exact. Since L is injective, this implies that image of 0 equals to kernel of L equals to 0. And since the last 0 is maps any element to 0, and P is surjective, this gives that image of P equals to kernel of 0 equals to co-image of F, which is A on kernel of F by definition. So it remains to show that image of L equals to kernel of P. I write at the top of this page, image of L is the set of all L of A such that A is in kernel of F. So this is equal to, since L is injection, so L of A equals to A, and image of L is the set of A such that A is in kernel of F, so this is kernel of F. So image of L equals to kernel of F. On the other hand, kernel of P equals to the set of all A in A such that P of A equals to the 0 of co-image F is kernel of F. This is the 0. 0 of co-image. The set of all A in A such that P of A equals to kernel of F. This is equal to the set of all A in A such that P of A is A plus kernel of F equals to kernel of F. And this is equal to the set of all A in A such that from group theory we know that A plus kernel of F equals kernel of F means A is in kernel of F. And this is in fact the set kernel of F. So compile. This one is kernel of F and this one is kernel of F. So the sequence is exact. Similarly, you can do this for this sequence and this sequence. Here is some remarks. 0ABF is an exact sequence of module homomorphism if and only if F is a module monomorphism. I explained about this. This is exact if image of A 0 equals to kernel of F. Image of 0 is 0. So this means kernel of, this is exact if and only if kernel of F equals to 0. And we know that kernel of F equals to 0 is equivalent to say that F is a module monomorphism. Similarly, BC0 is exact if and only if G is a module epimorphism. G is a module epimorphism. This is because image of G equals to kernel of 0. Kernel of 0 equals to C, and so image of G equals to C, and this means G is surjective, and so module epimorphism. If A, B, C is exact, then GF equals to 0. If A, B, C is exact, then GF equals to 0. Let me explain about this one. We know that if the sequence is exact, we have image of F equals to kernel of G. This means that for all A in A, F of A, which is in image, is in kernel of G. For all A in A, F of A belongs to kernel of G. This means that for all A in A, G of F of A equals to 0. This is equivalent to GF equals to 0. So exactness gives here that GF equals to 0. But not conversely. If GF equals to 0, we do not have that this sequence is exact. This is one direction. If this sequence is exact, GF equals to 0. You're welcome. I do not know what is the problem. I do not know what is wrong. Maybe your internet line, your net, or your system, or any other problem. I do not know. I think it is better to change your internet with more strong internet. Finally, if A, B, C to 0 is exact, then co-kernel of F is the quotient B on image of F is the quotient B on kernel of G. which is the co-image of G, which is isomorphic to C. This is an important property that if we have this exact sequence A, B, C to 0, co-kernel of F by definition is B is an image of F. This is only by definition. But since image of F equals to kernel of G by exactness, so I put kernel of G instead of image of F. This is B on kernel of G. We know that B on kernel of G is co-image of G. Co-image of G by definition. But since B is surjective, is an epimorphism, by the isomorphism theorem, by the first isomorphism theorem of modules, we conclude that since B to C is onto, B on kernel of G equals to image of this one. But this is the image is C since G is onto. B on kernel of G equals is isomorphic to C. So B on kernel of G, which is co-image of G, is isomorphic to C. Consequently, we have that co-kernel of F is isomorphic to C. Co-kernel of F is isomorphic to C. An exact sequence of the form. This form is called a short exact sequence, which is very important notion in the next subjects. We say that any exact sequence of this form is called a short exact sequence. Yes, Zaidun Saadun, dear Zaidun Saadun, I do not know what is really the problem. Since I do not know any professional information about the system. I am only a teacher, and as you enter to the system and work with the system, and I teach. I do not know. I'm not an engineer, and I cannot solve your problem. But in the system, there is a supporter that you report your problems to the supporter. I do not know. You know the supporter on the system or not? Yes, I understand what you say. Sometimes you have voice, but not picture. Sometimes you have picture, but not voice. Sometimes you see what I write at the end of some pages, or in some sessions you see my writing, and in other sessions you do not see my writings. I really do not know what is the problem. It seems that it is only your problem because the others do not report me such problems in the class. I think it depends on your net. Excuse me. You're welcome, dear Zaidun Sadun.
You are currently the only person in this conference.
Excuse me, I disconnected. Let me share the picture. Okay. Any exact sequence of this form is called a short exact sequence. Note that F is a monomorphism and G is an epimorphism. So in a short exact sequence, we always have F is a monomorphism and G is an epimorphism. And also image of F equals to kernel of G. The preceding remarks show that a short exact sequence is just another way of presenting a submodule. A is ISO to image of F and its quotient module B on image of F, which is equal to B on kernel of G, which is isomorphic to C. Here, in fact, A is a submodule of B. When you have F is a monomorphism, if F is a monomorphism, you can consider A as a submodule of B. Okay. So when you have, as I explained now, A can be considered as a submodule of B. So image of F is equal to A. A is isomorphic to image of F because F is one-to-one, and so A on kernel of F equals to image of F. But this is 0, and so this is equivalent to A. So A is equivalent to image of F. Image of F is a submodule of B. And its quotient module B on image of F. On the other hand, we know that B on kernel of G, which is image of F, equivalent to C. So on the other hand, A is a submodule of B by image of F, and on the other hand, B on image of F, which is A, is equivalent to C. We have a useful lemma, and which is it is a well-known lemma under the name of short 5 lemma. Short 5 lemma says that if you have two short exact sequence of modules and 3 homomorphisms that connect between the top and the bottom, alpha, beta, and gamma. If it is a commutative diagram means beta f equals to f prime alpha and gamma alpha equals to G prime beta, commutative diagram. Each row is exact. This is exact and this is also exact. So the first assertion says that if alpha and gamma are monomorphisms, then beta is a monomorphism. If alpha and gamma is monomorphism, beta is monomorphism. Number 2, if alpha and gamma is epimorphism, then beta is also epimorphism. And number 3 says that if alpha and gamma are isomorphism, then beta is also an isomorphism. This is a well-known lemma under the name of short 5 lemma. About the proof of this lemma, in the next session, we will discuss about the proof. I think it is sufficient for today, and we will continue the course with the proof of the short 5 lemma in the next week. Any question? If there is no question, I say goodbye to you and take care to the next